this morning, without going into details, that may have made some people feel a bit uncomfortable or unwelcome or been off-putting in the end of the last discussion. And, you know, without having a whole thing about it, I just wanted to make sure that we acknowledge that this is not the sort of thing that we feel is good for the community as we try to grow it and be more diverse and be more welcoming to people of all sorts. And it would be good to try to avoid these things in the future. When we talk about the bigger picture later on with the future of Haskell, we can have that discussion and how to go forward in a good way. But I felt the response right now, just to acknowledge this, and that this is not the sort of thing we want to be having in our discussions, is good. So thank you for your time.
Hello. I'm going to talk about our experience in teaching Haskell to undergrad students, and because there's an awful lot of co-authorship going on here, Tobias Nitko is my advisor, and he's also the lecturer for the course, and all these four other people have something to do with organization of the course, and they exercise in one way or another. So let's just get started with the setting and the syllabus of the course. It's compulsory for second-year students, and it's in general it's called Introduction to Functional Programming, and it's mandatory for computer science students and also information system and for teacher education. And also we also sometimes get students from other fields like mathematics and economics. So we have a very diverse crowd, but the majority is really in computer science. And in the previous years, the language chosen in the course varied a little bit. So we had OCaml some years ago, and we had standard ML, but when we took over this course, we chose Haskell. So the question is, why Haskell? Here are our main motivations for that. First and foremost, Haskell has a large user community and also real-world appeal. And what is very good for creating the lecture in the first place is that there's a variety of textbooks. But really one of the main selling points for choosing Haskell was quick check exists. And as you will see throughout this talk, we really made great use of quick check. This kind of looks like a little bit negative. It also has lazy evaluation, because in the beginning we were not sure how students would be able to deal with lazy evaluation, and it turned out to be not so bad. So what's the syllabus? You can have a short look over this. So there's nothing too controversial here, I guess, but I think at some points deserve some further explanation. So, for example, we really gave some emphasis on proofs, which might be because we're at the chair of logic and verification, and so we introduced structural induction on lists very early in the course, and it turned out that students were really able to deal with that just fine, and it gave a sense of that you can actually manipulate programs as mathematical objects, and that you're not just doing ad hoc programming like trial and error, but that you can really make some correctness proofs. And I mean, in the beginning, those were really simple, so like associativity of append or like this reverse append thing. And then we moved on to more general algebraic data types like trees and stuff like that. And we also introduced induction principles for them and did some similar proofs. And most of them were designed in a way that you only need equation reasoning and sometimes case splitting, but nothing too fancy, so no classical reasoning and things like that. And then also we had modules here. So we introduced the module system and said, for example, we have the abstract notion of sets here, and we're going to implement sets with lists. And then we are going to make a proof that our operation or concrete implementations of operations actually satisfy the invariants we posed over the sets. Also, we kind of had to make sure that students can actually do something with their programs. So we had to introduce I/O, obviously, and it's kind of similar now to Brandy Yoge's course at UPenn. We introduce I/O as some sort of opaque thing. We do not mention monads here. We just say this is I/O, this is how you use it, here's a do block, and this seemed to work pretty well. And we strongly emphasized the practical notion, so we didn't just do some like command line program, because they can already do command line programs. They can just fire out GHCI and type something, so this already pretty command line-ish. So we made them work with files and also with the web. So we, for example, in the lecture, we demonstrated how to fetch a website, and then we, as an exercise, we had them implement a simple chat server, and in the next week, a simple chat client. So that we really introduced these concepts right from the beginning, and we wanted to avoid this impression of Haskell, which sadly many students who have had no exposure to Haskell before coming to our course and thinking this about Haskell, so we need to get rid of that notion from the very beginning. All right, so now to the really interesting bit, because lectures are nice and all, but people still need to learn something and practice what they learn, and that's where we have also a strong emphasis on exercises. And the interesting bit about it is that we have had a competition, but more to that later. So we have weekly assignments. And these assignments consist of these parts. So we have a section on group exercises, which are discussed with the teaching assistant in a hands-on session, in a lab, basically. Then we have homework, for which students have 1 week time. And then we have a separate competition problem. So what do these tutorial groups look like? They each last 90 minutes and are led by a student TA. And in these years, we had about 20 to 25 groups, so you can see that we have like 10 to 12 or 13 student TAs, which is quite a lot, but we kind of like it because in general, around 10 people show up per session, so we can really get this hands-on experience. And the way they work is usually that the exercise sessions are explained, and then the students are supposed to work on them by themselves. And at the end of the session, they can exchange ideas about how they solved it. And only if they have problems, the student TA goes to them and helps doing this. Because it's of no help of like if someone stands in front of them and just explains them how to write their programs. That's not really much value. And we made very good progress with that. What about the homework? Usually like 3 to 4 problems, and the problem is that the time to solve them greatly varies. So we had to take great care to not make them excessively long, but it's very difficult because, as I said, we have a very diverse crowd. So naturally, people who have not had much exposure to programming before, who might not have had like students from economics, basically, for example, as opposed to students in computer science who have had much more exposure to programming before. And we had a system that the students could upload their submissions to our servers, and then a cron job basically runs a test suite periodically. And then this cron job basically executes some quick check tests, more to that later, and then mails the results of these runs to the students. And then the students can upload their solutions arbitrarily many times. And when the deadline is passed, the solutions are being graded by the student. So the grading is manual. So about the test suite. These tests are handwritten by us, and they check both against the specification of the problem and the reference implementation which we delivered for the problem. The tests and the expected results are secret, so that students cannot try to optimize for the tests. But if there's an input which fails the test, this is being reported to the students. The problem is with the default setup of quick check and running these tests, we had some issues with exceptions and non-termination. There's this within combinator in QuickCheck, but it's potentially confusing because sometimes it's not, for unexperienced students, it's not clear whether their test failed or if it's failed because of timeout. So it's not the problem, the real issue, underlying issue is sometimes obscure. So we had to tweak that a little bit, and it's the same for exceptions basically, and we used the control.spoon package, which really does a nice job of inspecting what went wrong in the test. Future work might be that we integrate additional style checks to our test suite, and this is really a point where we're not sure if that's going to be a good idea. So after my talk in the discussion, I would like to solicit feedback about if everyone has ever done that, and if it's potentially hurting the feelings of the students if it tells them all over again that like their style is wrong. Okay, lessons learned. We do need to make sure that the tests are not vacuous, because and this also applies to the exercise sessions, because in the exercise sessions too we urge students to write the quick check test. And it's really hard to explain to students that the quick check test they wrote, their polymorphic property, does not test what they think it tests. because it defaults to unit. So we have to tell them, and we have to do that as well, that you always have to instantiate your polymorphic properties with small types. Otherwise, your tests are vacuous. Also, we had to write a lot of generators by hand because oftentimes these test inputs were much too large or did not exhibit certain properties we wanted to. So quick check is nice, but you always have to tune you have to tune a lot. So when we were devising our test cases, we had to basically devise wrong programs as well, so that we could kind of anticipate what sort of programs would fail, and then tune our tests so that they could actually detect that failure. So the bottom line is, do not trust detective quick check alone. There's also detective small check, and you should make great use of both tools in combination, tweak to your problem at hand. Alright, so now about the competition. Our workflow was as follows. We usually picked a distinguished homework exercise and sometimes devised an additional exercise which was not part of regular homework. And we then fixed a ranking criterion. So, for example, we said solve this problem with as little tokens as possible, or solve this problem as efficiently as possible. And we even had 1 week where we gave grades for artistic value. Then we rank all student submissions, comment them, and publish good solutions. And at the end of the year, we made an award ceremony. And this was all run by Jasmine Blanchette, my colleague. And for this purpose, he gave himself a character figure called MC Hammer, and the master of competition. And he wrote his blog post about the solutions in a very self-important third-person style. And this really helped to get the students' attention because it was humorous and really went to great length explaining what were good solutions, sometimes mocking wrong solutions, but not never in an insulting style. So we did not pick on any people, but just so basically that we wanted to maximize the learning outcome from these posts. So why did we run this competition? This is a quote from Piotr Rybnicki. Yes, and we really think this is true. It's a lot of work to make these competitions, but in the end, the payback is that we can motivate some of the good students, and we even can convert some of them to be future Haskell programmers. So that's really a good outcome. So here's an example for this competition. You can just have a look at the task. So we put this reverse and alphabetic order in there that they just could not use standard library functions and not just like Google for a solution, but it's always a little bit modified. And this is from week 2. So students, some students have never heard of Haskell before. I mean, most students have never heard of Haskell before, and that's the winning entry. This was really impressive. This was also from a student who has been exposed to programming before, but not to Haskell. And what we can see here is that people go to great length in order to come up with very good solutions. They go to the standard library and like try to find everything which could be related to their problem at hand, and then they spend hours and hours of optimizing their solution so that they get as little tokens as possible. And that's really impressive for the second week in the lecture. So here's an example from later in the course where we did not count tokens, but where we valued efficiency. So we wanted them to write an AI player for Othello, and the criterion here was a tournament between all contestants. That took quite a while to evaluate, even just running the whole thing, because we gave them a timeout of 10 minutes per player, so we had 20 minutes per match. And we had quite a lot of submissions in the order of 35. So, 35 squared times 20 minutes. So we had to distribute it on our Isabel build cluster in order to be run in overnight. But this was really interesting also because here also people spend a lot of time in optimizing their solutions, and you could read through their comments, and it was really interesting to see that they dug into the theory, like writing min-max pruning on whatever they found necessary in order to win this competition. So yeah, that's one of the results. So they spend really a lot of time, and someone even put in the comments that they didn't sleep just to get their stuff into before deadline. And some of them even ignored all the other exercises, so they just did the competition exercises because these homework are not mandatory. And so yeah, they could just like do whatever they want to do. But yeah, ranking the solution takes a lot of time. But the real value behind this competition is that it's a vehicle to teach advanced concepts which are not part of the syllabus. So some of the better students easily get bored by the standard curriculum, and by giving a competition, we can teach them as well and keep them motivated to continue on their journey to Haskell. And as I also said, it fosters our exploration, and it's also rewarding for us in the direct sense because we get a lot of good students to implement projects like these. So this is quite a lot, and they have been helping us with Isabel, development of Isabel, and much more. And this is really good. So if you're running a lecture and you need good students for student projects, do a competition. So how about the exam? And without further ado, I'm going to show you two diagrams from the first two iterations of the course, which correlates the points gained in the homework with the points gained in the exam. And then let the numbers speak for themselves. So you can see x-axis. So we had this was the maximum number of points they could get in all the homeworks together, and this is the number of points they got in the examination. And every dot here is one student. So you can see that apart from a couple of outliers here, once they have a sufficient number of homework points, it's basically impossible to fail the exam. So this is this blue dashed line is the score they needed to pass the exam. And this is really impressive, because what that tells us that if we can encourage people to do their homework, not only do they really learn something, but the side effect is also that they pass the exam, so they also can progress in their studies. And here's the same thing for the second iteration of the course, and it looks kind of similar. There are a lot less dots here because we had about 100 students less in this course, just not because we were so terrible, but it's just like normal fluctuation in the student numbers. And yeah, so what we take away from that is that making homework is one of the best ways to prepare for an exam. It really doesn't matter if they just like, it really doesn't, it doesn't matter how long they take to prepare for the exam, they have to do homework. So you have to make the homework exciting and interesting and engaging.
Or mandatory. Or mandatory.
Or mandatory, yeah. Sure.
It also shows that if you don't do your homework, you still have a good chance to pass.
I mean, that's always the case. We always have a lot of dots here. So it kind of, the implication goes the way that if you do homework, you will pass, but not the other way around. So what worked well? Induction and equational reasoning was pretty well understood, and also list comprehension. So we introduced list comprehension very early in the course, and people thought that it's like the ultimate solution to everything. They tried to zip lists with list comprehension until they figured out, no, that's not quite how they work. But nonetheless, were very creative in coming up with list comprehension, which just like produce singles and values or whatever. It's the ultimate tool for everything. And also the I/O tasks in the exam were pretty well understood. I mean, you usually get some things like missing return statement, or sometimes some minor syntactic quibbles, but the problem is that in the exam they don't have access to a type checker or to a compiler, so these kinds of problems can happen. But in general, the idea of I/O was well understood. What did not work so well, yeah, here, type inference. We did not go full circle and teach the type inference algorithm. We just said like how to do type inference, to come up with some equations, and then kind of try to solve them. And we gave them simple things like map with a specified function, and then they should what they should come up with is that the type of that is like a list of specified type to some other type. And stuff like that didn't really work at all. People just forgot to instantiate variables. They forgot to remove arguments. Yeah, we have to do better in the next iteration of that. So if you have any idea how to teach type inference, I'd be very happy to hear that. Also higher order functions. So get one task in the exam where it says, here's a function defined via list comprehension, via explicit recursion, and via higher order functions, and people sometimes even boycotted the last one. I mean, they didn't even attempt to do it with higher order functions. And also evaluation order. As I said, we thought that lazy evaluation might be difficult for them to understand, but it turns out any evaluation order is hard to understand. So, and it's being a little bit complicated by the fact that although it's quite intuitive for experienced Haskell programmers, it's sometimes if you have like 5 plus 3 plus 8, and you tell them you just have to reduce the outermost radix, unless you're stuck. I mean, when you have some primitive operations, you have to reduce them first. So also input for teaching evaluation order would also be greatly appreciated. And with that, I'm done and happy to take questions.
All right, there's time for questions.
Do you have the data correlating the competition results with the passing score?
No, unfortunately not. But as I can tell you from, there are not at the end of the semester there are not many people left doing the competition. So around like 20 or 30 active students, and I can tell you that all of them passed. So, but I don't have any more specific data than that.
Do you use Safe Haskell or any Haskell external method to run possibly malicious code from the students?
So the idea was right now that we are running them on a virtual machine with in a sandbox environment, but we did not test anything else yet. And also, if people are able to write code as clever to escape from this stuff, we think they earn their grades.
You asked the question of how could you teach type inference better. I want to ask the opposite question. If you had the ability to change how Haskell does its type inference, would there be a way that you think the students would have an easier time with?
I'm not sure. It might help if we had more tools to visualize how type inference works. I mean, obviously you can't teach the whole thing because usually we ignore type classes in that setting and also some of the more advanced, all of the advanced type inference features. But what would help greatly is that if you had a way to tell GHC, please give me a trace of type inference which is like human readable, and then we could try to come up with visualizations on top of that, so that the students could see the real thing and not some like abstract theory where they create some equation systems or whatever.
Okay, let's thank the speaker one more time. Okay, next up we'll have a talk on type checking polymorphic units.